So we've learned a lot about force vectors, Newton's laws, all those kinds of things. Today we're going to take our idea of force vectors and free body diagram to another level. We're going to start looking at an example of how those things work. We're going to look at incline planes. The first problem we're going to look at actually has to do with this car right here. This car sitting on this incline plane. We're going to imagine an actual car going down an actual incline plane, and the idea is we want to find what is the acceleration of the car down the incline plane. We're going to start without friction, and then we'll add friction in and see how difficult we get. Okay, so here's the setup we're working with today with this incline lap. I've got an incline plane set up here with this ring stand. This allows me to adjust the height of the incline plane. That's one of the variables I want to look at today. I want to look at how does the acceleration work, how does it change when I adjust the height. The other variable I want to look at is what happens when I adjust the mass of the car. So I'm going to start putting 500 grams, a kilogram, all those kinds of things on this car to change the height, or change the mass. So there's two variables I'm going to look at. I'm going to look at what happens when I change the height of the ramp, or the angle of the ramp with the floor, and I'll do that by increasing the incline plane here. The other one is what's going to happen when I change the mass. I'm measuring the acceleration using a motion detector. So I have a card that I put on the car here. I'm going to start it about a half meter away. I'm going to hit collect, and then I'm just going to let it go. I've got a towel over there to stop the car so it doesn't hurt itself. So that's the setup for the lab. You're going to end up getting two different data files. One that has the velocity graphs that talk about the change in the height. The other one's going to have the velocity graphs that talk about the change in the mass. You'll need to find the acceleration from those graphs so that you can start to make some claims about how those variables affect the acceleration. Good luck. I'll get this data for you. Okay, one of the things you're going to have to keep in mind when looking at these data sets is they're not as clean as they used to be. So you can see in the velocity graphs, I don't know if you can see it on the picture there, but it gets kind of messy. The car hits the floor and it starts to do some crazy things. The position graphs look pretty good, but those aren't the ones that you need to analyze when you're looking for acceleration. So you're going to have to kind of look at both graphs to figure out the part of the graph that you want in order to find the slope of, in order to get the acceleration. Each one of these does have a nice increase here, not right at the beginning because it had to kind of pick up the car, but once it was rolling down the track, each of them have a good acceleration. So be sure you pick the correct part of the graph in order to find the acceleration. If you start to get all the messy stuff at the end, you're not going to come up with the right data for what you're looking for. Good luck. Let me know if you have any questions, and I will see you soon. So here's the situation. I got a car that's going down a 30-degree incline. The car has a mass of 1,200 kilograms. We're going to try to solve for the acceleration of the car down the incline. Once we find the acceleration, we can do all kinds of kinematic stuff if we want to find velocities or times or any of that stuff. But at least we'll get an acceleration so we'll know where we're going. So the first thing I'm going to do here is I'm actually going to draw a free body diagram. So we're ignoring friction in this case. We'll add friction in a little bit later, but for right now we'll ignore friction. If we look at the forces that are acting on this car, we have gravity, mg going down, and we have the normal force. Now if you remember, the normal force counteracts gravity, but it also acts perpendicular to the surface, which means the normal force is going to go up there like that. We'll call it F normal. Let me redraw that free body diagram. I don't like the way this free body diagram looks, okay? I have two vectors. They're not exactly on a perfect axis because we've got the 30-degree incline. But what I really don't like about this situation is the fact that the car is not going in the X direction or the Y direction. The car's going in both. I don't like that, okay? That's hard to do. I can't do a problem, or it's difficult to do a problem, if it's not going directly in the X and the Y. I like looking at X and Y independently of one another. here's a trick. This is what we're going to do. We are going to draw our XY coordinates. I just drew my XY coordinates along the inclined plane. You need to remember that this idea of a reference frame, this idea of a Cartesian plane or a coordinate plane is an imaginary thing. You can draw it anywhere you want. You can draw it from the top of the thing, the bottom of the thing. You can draw it at any angle that you want. So what we're going to do is we're going to actually draw our incline or draw our Cartesian plane at the angle of the incline. Now the car is going along the x-axis, at least the x-axis the way we drew it. If you just turn your head like this, that's what we're going to solve the problem. We're going to solve our entire problem with our head turned like this. Now, to not get a crink in your neck, I'm going to redraw this to look like this. So if I redraw this, the normal force is going right along the y-axis. I like that because I don't have to do any trig. Gravity, mg, is going right, not on an axis. But we do at least know the angle. So let's see if we can't figure out that angle. This angle right here, okay, if you look at, there's kind of a triangle here with the 30. 30, this is 90, which makes that 60. That makes this 60 degrees, which makes this 30 degrees. So our 30-degree angle is actually down here between the y-axis and our vector. So this is a great way to do these problems. You're going to draw your axes to go along the inclined plane, and then you're going to tilt it so that it looks good. So you can see now that this component, here's mg, the force of gravity in the x direction here. The force of gravity in the x direction is what's pulling this thing down the inclined plane. The force of gravity in the y direction is actually going to cancel out with the normal force. My normal force here is probably a little bit big. That's going to cancel with the normal force. So we don't care about that right now. We do care about the force of gravity in the x direction. That's what's going to, that is what's going to pull this car down the inclined plane. So if we do some trig, this is 1200 times 9.8. So 1,000 or 11,760 newtons is the force of gravity. The force of gravity in the x direction is going to involve some trig. So we do the sine of 30 times that, and we get 5880 newtons. So we get 5880 newtons pulling it down that way. I could do the trig to find this force of gravity in the y direction, but I don't really care right now because it's going to cancel with the normal force because the car is not moving in this direction. It's not moving off of the inclined plane or into the inclined plane. It's moving along the inclined plane. So I got my 5880. That is the net force. That's the total force. This is the only one that's left over. That's what's pulling the car down. So F net is 5880 newtons, which equals 1200 times A. A is going to be 4.9 meters per second squared. It's being pulled down the inclined plane at 4.9 meters per second squared. This is a pretty classic standard inclined plane problem. Okay, so let's take a look at one that does have friction in it. So we're going to kick this up a notch just a little bit to add friction. And you're going to see that this idea of tilting our axes actually makes it a lot easier than keeping them side to side, even when we add friction. So this is what I've got. I got my same 1,200 kilogram car. I got my same 30 degrees, but this time I'm going to add a coefficient of rolling friction, or we'll call it, in this case, call it kinetic friction, or rolling friction, I guess. Our coefficient of friction is 0.1. So we do have some friction in the car as it's going down the inclined plane. How do we solve this problem? So let's start by drawing our free body diagram. If we look here, I'm going to draw my axes this way. I got a normal force going up there. I got mg going straight down. And the force of friction is going backwards. It's going backwards along the inclined plane. So let me redraw that so that I don't have to tilt my neck. This is our free body diagram. So let's try to analyze or kind of rectify this free body diagram so we can find our net force. So if we look here, we've got the same gravity we did before. So what was that, 760 newtons going that way. This was 5880 newtons going that way, doing the trig. I'm going to have to do some trig to find the other side because this normal force is actually going to be somewhat important this time. So 11,760 times the cosine of 30 is 10,184. That makes this 10,184 newtons. Okay? So, these are the forces that I know so far. I know the normal force is the same as this right here. I know that this is the force that's going to be pulling this down. But this force is also going to compete with the force of friction because one's going one way, one's going the other. I'm looking at X and Y independently of one another. So how do I find the force of friction? Well, the force of friction is equal to the normal force times mu. I gave us mu. So the force of friction is going to equal 10,184 times 0.1, which gets us 10,108.4. Just call it that. So this is 1,018 newtons. So look what's going to happen here. I've got 5,880 pulling this way. I got 1,018 going that way. Who's going to win? Well, the 5,000 is going to win. This 10,184 cancels with that, so I don't care anymore. This 11,760 doesn't make any difference because I broke it into components. I'm looking at those. So the only two that actually are left over are the force of friction in the x direction, or I'm sorry, the force of gravity in the x direction, and the force of friction in the x direction, which happens to be negative. So my net force, F net, is going to equal the sum of all the forces. The up and down forces don't matter, so I'm going to just ignore those. So I got 5880 newtons plus a negative, or I can just take minus 1018 newtons. If I do that, I take my 5880 minus 1018, I get 4,862 newtons. That's the net force. That's the total force that's going down. Notice it's less than the 5880, which we had last time, because we have a little bit of friction here that's going to slow us down a little bit. So how do I find the acceleration of this thing? I do this is equal to ma, 1,200 times a, and the acceleration is 4.05 meters per second squared. So 4.05 meters per second squared is less than the 4.9 meters per second squared that we had last time, but we added friction, so that makes some sense. At this point, I could ask you all kinds of questions. Things like, how far does it go after 2 seconds? How fast is it going after 5 seconds? After it goes 12 meters, how fast is it going, or how much time does it take? All of those kinematic things are just like what we did in the first unit. Once you find the acceleration, you can do those kinds of things. So this is a pretty complicated actually problem dealing with friction and dealing with inclined planes. The key here, and the key to all of these problems in dynamics, is finding a free body diagram, rectifying it to find the net force, and then using that net force to do some kinematics. So you noticed that in this problem, we had lots of variables that did make a difference. The angle definitely made a difference when we solved that problem. If this thing were inclined at a much higher angle, you're going to have a higher acceleration. Note, how high does the acceleration actually get? Well, we probably found this in our lab, that it actually starts to taper off and asymptote. Because if you had this thing straight up and down, the acceleration is going to be 9.8, which is just like as if it were falling. So the acceleration can't be over 9.8. So actually, if you looked at the acceleration versus the angle, as the angle got up to 90, the acceleration should get up to 9.8. What about the mass of the car? If you notice in our problem, we had mg as the force of gravity pulling the thing down. And then when we tilted it, mg was actually pulling the car along the incline plane. We used some trig to solve for the force of gravity in the x direction, and then we used that to solve F equals ma. Well, think about that a second. We had mg times the sine of theta to get the force in the x direction is equal to ma for the acceleration. What happens to m if you have it on both sides of the equation? M actually goes away. You don't need that. Mass does not make a difference when you go down the incline plane. And hopefully in your lab you found that. That's one of the things that you should have seen in the data, was that even though we doubled or tripled or quadrupled the mass in the lab, the acceleration didn't change appreciably as much. Okay, good luck with the rest of your worksheet. Let me know if you have any questions, and I'll see you next time.